Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Mind Maps, we'll be dealing with the very first chapter of chemistry in the syllabus for grade 12 students in CBSE. The chapter that we'll be dealing with is the solid state. And as usual, we're getting the help of this mind map in order to explain this chapter. Mind maps are really useful as tools for last minute preparations. However, they can be very expensive. So this video is devoted into explaining this mind map in some detail to simplify it. So today we'll be looking at the chapter, the solid state. It's a pretty important chapter and it involves a lot of visualization. So first of all, the solid state. Matter contains three common states. So matter is existing around us in three common states: solid, liquid, and gas. We all know this. Liquid and gas, according to our grade 11 syllabus, are classified as fluids. So today we'll be learning about the solid state. Now this is the state of matter which has definite shape, definite volume, and definite mass. It also has short intermolecular distance and strong intermolecular forces. The constituent particles of solids are at fixed positions which can vibrate or oscillate. However, they cannot move from one position to another permanently. Solids are rigid and incompressible. So today we'll be looking at first the types of solids, crystalline and amorphous, and their various subtypes. Then we'll be looking at a crystal lattice and more details about the unit cell of a crystal lattice. Then we'll be looking at packing efficiency of particles and voids, which are the empty spaces between them. Then we'll be looking at electrical and magnetic properties of solids. And finally, we'll be looking at imperfections, which can affect solids. So first, let's move on to the types of solids. Solids are basically classified into two types. The first one is amorphous solid. Now, what are amorphous solids? Amorphous solids are solids with irregular shaped particles. These are also known as supercooled liquids. And they have a lot of properties. First of all, irregular shape. Then they have a broad range of melting point. So if you want to say the melting point of an amorphous substance such as glass, then you must quote a range of temperatures. And when they get cut into two pieces, then the two pieces have an irregular surface when cut. So the surface that's between them is now irregular. And when you cut these amorphous solids, you do so with a sharp edge tool. And amorphous solids, they don't have definite heat of fusion. And another interesting property about amorphous solids is that they are isotropic. Now this means that they have the same value of physical properties such as density, mass, and say bond length, etc., across all the directions. And this is due to the fact that amorphous solids are usually mixed, which means that they also have short order. So if you start counting the solids and trying to arrange them in a definite order, then the definite order runs short. It does not apply for the whole of the amorphous solid. So because of this property, amorphous solids are isotropic, which means that they have the same value of physical property across all directions. The second type of solid is known as crystalline solid. This contains large number of small crystals with definite shape. These solids are known as true solids, and they have a definite geometric shape, and they also have sharp melting point. So if you want to quote the melting point of a crystalline solid, you quote a specific point. However, for an amorphous solid, you have to quote a range of temperatures. And when they get cut into two pieces, they have smooth surfaces. When you cut a crystalline solid with a sharp edge tool, then the cut surface is actually smooth, as opposed to irregular when you cut an amorphous solid. Then crystalline solids, they have definite heat of fusion, so you only need a specific amount of heat in order to melt a crystalline solid. However, for an amorphous solid, it is actually a range of temperatures, so therefore there is no definite heat. And because of the fact that crystalline solids have a long range order, which means that they consist of one unit cell repeating over and over and over again, they have this unique property of anisotropy, which means that when you look at a particular quantity, physical quantity, say density or bond angle, etc., and you try to look at it from two different perspectives, then the value of those quantities in a crystalline solid stays different. It is because they have equal spaces between the particles. So when you look at it from an angle, then this property's value starts to differ. This is known as anisotropy. However, crystalline solids are further divided into many other components. The first one is metallic solids. Metallic solids are basically metal atoms which are held by a metallic bond. So these are a collection of positive ions which are held by a sea of negative electrons. And these negative electrons are mobile and they are free. Now, metallic solids are usually hard, but they are also malleable and ductile, just like the properties of metals. And metallic solids are also known for being good conductors. And metallic solids also have a high melting point. Next, we look at covalent solids. Covalent solids are solids which are basically nonmetals held by a covalent bond, sharing of electrons. Now, nonmetals are usually hard and they do not conduct electricity, so they're insulators. And these insulators also have a very high melting point. And atoms in covalent solids are bonded to each other using covalent bonds. Examples include silicon carbide and allotropes of carbon, which include diamond and graphite. For metallic solids, examples include metals such as iron and copper. Now, in terms of covalent solids, there is a general exception, which is graphite. So graphite has none of these properties that characterize covalent solids. For example, graphite is soft, it is a conductor of electricity, and it has fairly low melting point. The reason being that it is composed of parallel sheets of carbon. So therefore, the bond between the sheets, it's actually very weak. They're only bonded by dispersion forces or intermolecular hydrogen bonds. So therefore, graphite can be very easily cut. It is also soft due to this reason, and therefore the electrons can also go free of graphite's carbon atoms. So therefore, graphite is also a conductor of electricity. Next, we look at ionic solids. Ionic solids are basically composed of ions which are held by strong Coulombic forces. Coulombic means they're also electrostatic forces. So the ionic solids are characterized by hardness, but they're also brittle. So these solids are hard, but they also get broken up easily because they're brittle. And when it comes to ionic solids, in the solid state, these are insulators. However, in the fluid state, they are conductors. And ionic solids also have a high melting point. And finally, we look at molecular solids. molecular solids are basically composed of molecules which are held by intermolecular forces, which are basically van der Waals forces. So therefore, molecular solids are actually quite soft. But not, these molecular solids are further divided into three. The first type is nonpolar solids. The nonpolar molecular solids contain atoms or molecules. These are held by dispersion forces or London forces. So weak van der Waals forces are used to hold these up. And they are soft, which is general property, and they are insulators, which means they do not conduct electricity, and they have a low melting point. Next, we have polar molecular solids. So the reason why they're called polar is that the molecules here are held by dipole-dipole interactions. So the molecules which are present here are dipoles, so they have polar interactions, and that's why they have properties such as softness, and they're also insulators, and they have a low melting point. However, it's not as low as nonpolar molecular solids. Examples for nonpolar molecular solids involve noble gases such as argon and helium in their solid state, and molecules held by dipole-dipole interactions include water, hydrochloric acid, sulfur dioxide, etc. Finally, we have hydrogen-bonded molecular solids. These are molecules which are held together by hydrogen bonding. So dipole-dipole interactions contain HCl and SO2. However, when molecules are bonded together by hydrogen bonding, they contain water. So water is a good example of hydrogen bonded molecular solids. Polar molecular solids involve HCl and SO2. Now in here, H plus goes into one end and Cl minus go into one end, forming a dipole. And finally, when we look at properties, hydrogen bonded molecular solids, they are unusually hard. Ice is hard. Then they are also insulators. However, they are also having low melting point. So in that case, they are similar to the other molecular solids. So this is an overview of all the various types of solids. So we looked at amorphous solids and crystalline solids. That's the basic difference. Crystalline solids themselves have metallic, covalent, ionic, and molecular solids. We looked at that then. And molecular solids by themselves are divided into three, so that they are non-polar, polar, and hydrogen bonded molecular solids. So that concludes the types of molecular solids. Next, we look at a crystal lattice. What is a crystal lattice? Now, in solids, there is a main characteristic. So crystalline solids have a unique characteristic of regular and repeated pattern of constituent particles. So the constituent particles in a crystalline solid are composed of regular and repeated patterns. So a crystal lattice is what makes this repeated pattern. So what is a crystal lattice? A crystal lattice is a regular 3D arrangement of points in space. The points represent the molecule or the atom whose solid has the crystal lattice, and the lines represent the bond between them, the interaction between them. Now, crystal lattice is a general pattern. Each pattern has one unit, and a crystal lattice also has its smallest unit. This smallest unit or portion is called the unit cell. So a unit cell is the component which gets repeated to form a crystal lattice. Unit cell have many types. So on the basis of their centers, we can classify them as primitive, body-centered, face-centered, and end-centered. And other than that, there are also other kinds of lattices, such as the Bravais lattice, where 14 kinds of unit cells are possible. So when we look at unit cells based on the atoms, the first type is primitive unit cell. A primitive unit cell is a unit cell which contains atoms at only the corners. So particles are only present in the corner positions. And these primitive cells have 8 atoms because for a cubic cell, it is 8 corners. So the atoms are present in these 8 corners. And each of the atoms here are shared by 8 unit cells. So they have 1 by 8 times 8. So only one atom is totally present in a primitive unit cell. Now, these primitive unit cells can be divided into 7 types based on their axial length and their axial angles. So axial lengths include A, B, C. They're represented by that. And the angles are represented by alpha, beta, and gamma. The first type is cubic unit cell. Now, in cubic unit cell, there is the axial length is equal on all 3 sides. So A is equal to B is equal to C. And all the angles are corresponding to 90 degrees. So alpha is equal to beta is equal to gamma is equal to 90 degrees. Now, primitive cells, the primitive cells can undergo this shape. Body-centered cells can also undergo this shape, and face-centered cells can undergo this shape. Now, about the others, let's look later. The next kind of structure is tetragonal. Now, in tetragonal, we have 2 of the axial lengths as equal, but they're not equal to the third one. So A is equal to B, which are not equal to C. However, all of the angles are still 90 degrees. So as you can see, this is cubic. However, in tetragonal, the length of gamma is different from the others. And primitive cells and body-centered cells can also undergo tetragonal shape. Now, examples for cubic include sodium chloride and copper. For tetragonal, we have examples of tin oxide and titanium oxide, tin dioxide and titanium dioxide. Next, we look at orthorhombic. Now, molecules of KNO3 and BaSO4, potassium nitrate and barium sulfate, undergo orthorhombic shape. Now, this is the diagram for an orthorhombic shape. The characteristic here is that none of the sides are equal. So over here, there is a rectangle face, and then there is a cuboid. So the cuboid has none of the sides as equal. So A is not equal to B is not equal to C. However, the angles are still the same. So the angles are equal to 90 degrees. Now, orthorhombic unit cells can be primitive, they can be body-centered, they can also be face-centered. And the examples include KNO3 and BaSO4. Next, we have hexagonal unit cells. So this is hexagonal unit cell. So as you can see, it's in the shape of a hexagon. And the reason for this is that A is equal to B, but not equal to C. So as you can see, the hexagon is a regular hexagon. However, the depth is not equal. So A is equal to B, which is not equal to C. And over here, 2 of the angles, which is alpha and beta, they are of 90 degrees. So that means the angle between the top face and the lateral sides and the angle between the bottom face and the lateral sides are equal. However, gamma here is equal to 120 degrees. And that's why there is a shape of a hexagon. It consists of a shape of hexagon. And examples for hexagonal unit cells include ZNO, zinc oxide, and CDS, cadmium sulfide. The hexagonal cells can only be primitive unit cells. They cannot be body-centered or face-centered. Only primitive cells, that is, only the atoms are present at the corners and nowhere else. Now, let's look at the next type of primitive unit cell. This is called rhombohedral or trigonal, and this is the shape here. Now, examples include calcium carbonate and hydrogen sulfide, and the characteristic here is that all of the sides here are equal. A is equal to B is equal to C. All the axial lengths are equal. So therefore, this looks kind of like a rhombus because the angles, while they're equal, they are not equal to 90 degrees. So the problem here is that in a cubic, all of the angles are equal and all of them were equal to 90 degrees. Here, all of the angles are equal. However, they're not equal to 90 degrees. They are of a different angle, but all of the angles are the same. And once again, this can only be formed by primitive unit cells. Next, we have monoclinic. The structure of monoclinic is this one. And examples include monoclinic sulfur and sodium sulfate. This is sodium sulfate, not sodium carbonate. So sodium sulfate. Sodium sulfate and monoclinic sulfur are examples of solids with monoclinic structure, and they have monoclinic unit cells. Now, in this case, alpha is equal to gamma is equal to 90 degrees. However, beta is not equal to 90 degrees, as you can see here. And therefore, this looks like a parallelepiped. And over here, the sides are also different. So A is not equal to B is not equal to C. Finally, we have the structure called triclinic unit cell. And when it comes to monoclinic, primitive cells and end-centered cells can form monoclinic structure. Triclinic unit cells do not have the same side. So A is not equal to B is not equal to C. The axial lengths are different. And the angles are also different from each other. So in triclinic, all the angles are different from each other and they're never going to be 90 degrees. And in case of triclinic, only primitive cells can form triclinic. Examples include potassium dichromate and hydroboric acid. Hydroboric acid and potassium dichromate. Dichromate are solids which contain a triclinic primitive unit cell. So these are the 7 ways in which we can form a unit cell. So these shapes are all applicable for primitive. Some of these may be applicable for end-centered, body-centered, face-centered, etc. But what are centered unit cells? Centered unit cells means that they have a center which is occupied by an atom. This center may vary, as we can see. In body-centered, there is one particle or atom at its body center and at its corners. So as you can see, there is an atom here, and there are atoms on all these 8 corners. This is a body-centered unit cell. For a body-centered unit cell, in addition to the 8 corners, since there is an extra one inside, there's an extra atom inside, we can say that a body-centered unit cell has 2 atoms inside it. Next, we move on to face-centered unit cells. In face-centered, all of the atoms are present, 1 at the 8 corners and 2 at the centers of each face. Center of each face. Up, down, left, right, front, back. All of these have an atom at its center, at the center of that face. In addition to which, they also have atoms at their corners. So for atoms at their face, the sharing ratio is 1/2. So half of an atom is going inside and half of an atom is going outside when it's at the face center. So therefore, since there are 6 of those, there will be 3 atoms plus the one formed by the 8 corners. So therefore, we'll have 4 atoms for face-centered. End-centered unit cells contain 1 particle at the center of any 2 opposite faces and at its corner. This has, again, 2 atoms because 2 of these times 1/2 gives 1 atom plus 1/8 times 8 gives 1 atom. So 2 atoms are present in an end-centered unit cell. So that concludes the unit cell, the crystal lattice by itself, and about its smallest unit, the unit cell. And we also looked at the various types of unit cells, which are primitive and centered. Primitive cells can be classified into 7 shapes, which are cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic. These are based on the axial length and the axial angle. And when it comes to centered unit cells, due to the center, there are three types again: body-centered, face-centered, and end-centered. Body-centered means the particle is present at the center of the cube, and face-centered means there's a particle at the center of each face, and end-centered means there is a particle at the center of any two opposite faces. So that means it can be top-down, it can be left-right, it can be front-back, but only two at a time. When it comes to density of a unit cell, we can measure it by the formula Zm divided by a cubed times Na. Here, Z stands for the number of atoms present in the unit cell. So that means for, say, primitive, it'll be 1. For face-centered, it'll be 4. For body-centered and end-centered, it'll be 2. Capital M stands for molar mass. A cube, which is the formula that we use for the density for the volume of a cuboid, means just that. So A cube means volume of the unit cell, the total volume of the unit cell. And Na is a constant, which is the Avogadro's number, 6.022 into 10 raised to 23 particles. Which they can be atoms, they can be dipoles, they can be molecules, anything. However, the value is 6.022 into 10 raised to 23. So that was an overview about the crystal lattice and the unit cell. We also learned about the density of a unit cell. Next, let's look at packing efficiency. So in solids, we have close packing of constituent particles. And when it comes to constituent particles, they can be packed in 1 dimension, they can be packed in 2 dimensions, they can be packed in 3 dimensions. In 2 dimensions, the main packages include square and hexagonal. Square means that 1 atom touches with 4, and for hexagonal, 1 atom touches with 6 other atoms. When it comes to 3-dimensional, we have classified them based on layers. So AA, ABAB, and ABC, ABC. So that means in AA, the layers on the top and the bottom are the same, while in ABAB, the second layer tries to occupy the voids left by the first layer, and in ABC, the third layer will try to fill the voids which are occupied by the second layer. The second layer is trying to fill the voids occupied by the first layer. So that is why it is called ABC, ABC. So these are all the various ways in which we can closely pack constituent particles in a solids. However, in whatever way we pack them, there is always some free space left. Because of the spherical nature of atoms and the cubic nature of the unit cell, there's always going to be some space left over. And these spaces are known as voids, and we'll look at them in a different section of this video. So for now, let's look at what is packing efficiency. So packing efficiency refers to the percentage of total space of a unit cell which is filled by particle spheres. Now, the general formula that we use here is packing efficiency is equal to volume of atoms in the unit cell divided by total volume of the unit cell times 100, because this is a percentage. When it comes to square closed packing, in square closed packing, all of these layers, they are of AA type. So the same layer is constantly repeated. So when the same layer is constantly repeated, we can notice that one edge length contains 2 times the radii of each atom. So A, the edge length, is equal to 2r. So when A is equal to 2r, what happens is that we get the formula 4 by 3 pi r cubed divided by 8r cubed. Now here the volume of atoms refers to the atoms which occupy a unit cell. So for a simple cubic, it will be just 1. So this is the formula, and the value that it gives is 52.4%. And this packing efficiency comes in elements such as polonium. So polonium, which uses a square closed packing efficiency, has a packing efficiency of 52.4%. 100 minus 52.4% will give you the vacant space kept by polonium or any other material which uses square closed packing. Now let's look at BCC, which is body-centered cubic. Again, this kind of uses square closed packing. So in a BCC, we know that there are atoms at the corners, but there's also an atom at the center. And all of the atoms at the corners, they touch the atom at the center. So the diagonal of a cube, which is root 3a, it'll be equal to 4 times the radius. That is the formula here. So the body diagonal is equal to 4 times the radius of an atom. So therefore, root 3a is equal to 4r. So therefore, a is equal to 4r by root 3. So for a BCC, the formula is 8 by 3 pi r cubed divided by 64 divided by 3 root 3 r cubed times 100. Remember, there's also a times 100 here. So that gives you a value of 68%. So 68% of a body-centered cell is a body-centered cubic cell is occupied with atoms. And over here, the number of atoms is 2 because 8 corners plus 1 atom at the center. So 74%. I mean, no, 68%. 68% is the value for this cell. The next kind is cubic closed packing or face-centered cubic. Again, for this one, we use the diagonal of one side of a cube. So over here, the formula is root 2a is equal to 4r. A is equal to 4 by root 2r. So when we look at the formula, volume of the atoms present in this cubic cell divided by total volume, the value becomes 16 by 3 pi r cubed divided by 2 root 2 r the whole cube times 100. So that gives you a value of 74%. So 74% of a cubic closed packed cell contains the atom in question. So for BCC, the examples include lithium and sodium. For CCP, the values include copper and silver. For HCP, which is hexagonal closed packing, we again get a value of 74%. And the examples include magnesium and zinc. Now let's look at the empty spaces between the spheres in a unit cell, the so-called voids. So the voids are the consequence of the arrangement of particles of a solid in layers. So when we arrange something in layers, we always get some spaces in between because you cannot arrange a sphere completely into a box. So there'll always be some spaces behind. And so these spaces, when it comes to atomic levels and solid levels, we use the term voids. So voids, again, are 3 types. So first of all, we have trigonal voids. In trigonal voids, we have 3 spheres in contact. So sphere 1, sphere 2, sphere 3. There is a void here. And this void is called a trigonal void because it has contact with 3 spheres. And the value that's given here, 0.155 to 0.255. This is the value of the radius ratio, and it is defined as the radius of cation divided by the radius of the anion. And the value of this radius ratio, it tells which void is present. So when you have a radius ratio of 0.155 to 0.255, it will always be a trigonal void. 3 spheres will be in contact. The next kind of void is known as tetrahedral void. As you can see, there are 4 atoms which line a tetrahedral void. So we have three atoms together. We add a 4th one on top of it, and therefore you get a tetrahedral void like this one. And when we look at tetrahedral voids, they occur when the radius ratio of the solid lies between 0.255 to 0.414. And they have 4 spheres at the vertices of a tetrahedron. So if we consider the void as a tetrahedron, then we have spheres on all the 4 corners, 1, 2, 3, 4. And when they touch each other, they leave behind a small space, and that space is what we call a tetrahedral void. When it comes to octahedral voids, we have 6 spheres which are touching this void. So that means the shape of the void represents an octahedron. So we have 3 cells on one layer, and there are 3 cells on the other layer in the opposite, in the inverted position. So when they join together, you get something like an octahedron here. So when you try to draw the atoms on the vertices of this octahedron, you will get the idea of an octahedral void. That is the space right here, when all of these atoms touch each other in this configuration. In octahedral voids, there are 6 spheres at the vertices of an octahedron. So the radius ratio lies between 0.414 to 0.732. So these are this is a general overview of the 3 types of voids that are commonly found. So a trigonal void has 3 spheres in contact, tetrahedral void has 4 spheres in contact, and octahedral void has 6 spheres in contact. So when we have a solid of n cells, say n atoms. So we have, say, a solid which unit cells, it contains n atoms. The number of tetrahedral voids will be equal to 2n, and the number of octahedral voids is equal to n. So suppose we have a face-centered cubic cell. Now a face-centered cubic cell will have 4 atoms inside that unit cell. So therefore the tetrahedral voids will be 8 and the octahedral voids will be equal to 4. That is the general idea. Next, we look at some of the properties of these solids, basically the electrical and magnetic properties. When we look at electrical properties, these electrical properties, they are based on the gap between conduction and valence band. So when it comes to solids, they organize their electrons in conduction band and valence band. And when you're able to transfer electrons from a conduction band to a valence band, then you will find that the material will be a conductor. In conductors such as copper and aluminum, we have overlapping or very small gap between conduction and valence bands. Like, for example, here. Here you can see that there is very little gap, and over here you can see that the bands have actually overlapped, so there is easy passage for electrons. So therefore, these materials, they can conduct electricity. When it comes to insulators, insulators have the exact opposite effect. They have a small energy gap between the conduction and valence band. So insulators, they have a large gap, to be exact. So they have a large gap between the conduction band and the valence band. So you can see here, there's a large energy gap in between them. So electrons cannot jump from this band to the other. So most of the times the valence band is empty while the filled band is usually the conduction band. When we look at semiconductors, semiconductors contain a small gap. There's a small energy gap between the conduction band and the valence band. So by itself, there is only limited conductivity for semiconductors. So semiconductors are usually limited in conductivity. But these semiconductors, they can be made conductive. So they're made to be conductive by adding some impurities. And these addition of impurities is known as doping. So once you have doped a semiconductor, you can actually fill the small energy gap, and therefore the electrons will now be able to travel from the conduction band to the empty valence band. Now, the type of filling the small energy gap gives us different types of semiconductors. You have N-type semiconductors or P-type semiconductors. N-type means you have negative charge. P-type means you have positive charge. There's a reason behind it. In an N-type semiconductor, you add group 15 elements. So group 15 elements have more electrons than group 14 elements. So the impurity is electron rich. So therefore, there is an excess of negative charge. When it comes to P-type, you add group 13 elements as the impurity. So when you add those, then you can see that there is a deficiency in the number of electrons. So therefore, there is an overall positive charge. So astatine is normally used for N-type semiconductors, while boron is used for P-type semiconductors. Once again, the reason why it's N-type or P-type is dependent on the amount, on the type of impurity that we add. If we add group 15, then the impurity is electron rich, so there is overall negative charge. If we add group 13 elements, then the conductor becomes electron deficient, so there is overall positive charge. So that's how you can bridge the small energy gap for semiconductors in order to make them conductive. However, this can also be made by also changing the conditions for temperature and pressure, making semiconductors into superconductors. Now, let's look at magnetic properties. In terms of magnetic properties, we have basically 5 kinds of solids. The first kind of solid is known as paramagnetic solid. Paramagnetic solids are weakly attracted, and they have unpaired electrons. So in paramagnetic, we have one or more unpaired electrons which are attracted by the magnetic field. So since the number of unpaired electrons is less, we have weakly attracted substances as paramagnetic. Examples include solid oxygen or Cu2+. Next, we have diamagnetic substances. So in diamagnetic substances, we have one or more unpaired electrons. No, that is the case for paramagnetic. In terms of diamagnetic, the situation is that all electrons become paired. So in diamagnetic substances, all of the electrons are paired. So it now starts to cancel the magnetic moment present inside the electrons, present due to the electrons. So now the diamagnetic substance it repels magnetic field. Next, we have ferromagnetic substances. Ferromagnetic. In ferromagnetic substances, the particles are strongly attracted to the magnetic field due to the fact that they form domains in the same direction. So in ferromagnetic, once again, we have unpaired electrons. However, the number is so many that they are actually arranged in the form of domains. Now, domains usually are helter-skelter. So in a domain, the particles go in one direction. However, amongst the domains themselves, there is different directions. When there is a magnetic field, they are arranged, all these domains are arranged in one direction due to that magnetic field. And that's why ferromagnetic substances are very good at being made magnets or being attracted to magnets. Examples include iron and cobalt. And for diamagnetic, we have examples of water and NaCl. Next, we have anti-ferromagnetic substances. When it comes to anti-ferromagnetic substances, the domains, which contain the unpaired electrons, are now present in the opposite direction. So because of the change in direction, now that cancels the magnetic moment. So the magnetic moment gets canceled. So the domains now become opposite and equal. So therefore, the magnetic moment gets canceled due to the magnetic field. An example for an antiferromagnetic substance includes manganese oxide, MnO. Mg stands for magnesium, Mn stands for manganese. MnO is manganese oxide. The final type of magnetic property is ferrimagnetism. So ferrimagnetic substances have unequal domains. So some of the domains point towards the magnetic field, others point away from the magnetic field, and the number of these domains which are for and against the magnetic field, that number is unequal. So therefore, we have weakly attracted substances as ferrimagnetic. Examples include Fe3O4 and MgFe2O4. These substances are ferrimagnetic because their domains are both parallel and anti-parallel, and the number of parallel and anti-parallel domains are unequal. So therefore, there is either a weak attraction or a weak repulsion due to the fact that the domains become unequal. Finally, we move on to imperfections in solids. All solids, especially crystalline solids, have an order or pattern for arranging their particles. However, even with this order, there are still defects found in solids. These defects are known as imperfections, and they come in two types. The first type is point defect, and the other type is line defect. In point defects, there is a deviation of ideal arrangement of solids at a single point. And point defects are usually stoichiometric defects. Now, these defects do not disturb the stoichiometry. So that means the formula of the solid stays the same. There is no difference in the stoichiometry. Now, stoichiometric defects are usually applied to non-ionic solids. The types of stoichiometric defects include vacancy defect and interstitial defect. When the lattice sites, which are supposed to be filled, become vacant in non-ionic solids, we call the defect as a vacancy defect. So let's say A, B, and then over here where it was supposed to be B, it's missing. And then we have A, and then B, and then A. So there is a vacant lattice site. So that is called vacancy defect. The next kind is interstitial defect. So the particles which are already present, now they start to occupy the interstitial site. So suppose we have A, B, then A, this is blank, A, and B. So the particle is not missing, it is present here. It is present at the interstitial site. It hasn't gone anywhere. However, it's not in its particular position either. So there is a defect, which is known as the interstitial defect. Again, this only happens in non-ionic solids. For ionic solids, we have a separate kind of defect known as impurity defect. So impurity defect, they are present in ionic solids and they are similar to point defects. So examples, we have SrCl2 and AgCl are as foreign atoms present in a crystal lattice. So for example, SrCl2 and AgCl, we have foreign atoms present in between them, forming impurities. The types of impurities are Frankel defect and Shotkey defect. So in Frankel defect, the smaller ion is getting dislocated to the interstitial site. So that means that the ion is already present here. However, it is now getting dislocated to an interstitial site. So there is no change in density. And there is no change in density. The other kind of defect is known as Shotkey defect. So over here, the charge stays the same. However, there is a loss of both kinds of ions. In Frankel defect, the ions haven't gone anywhere. They're still inside the solid, however, at the interstitial space. In Shotkey defect, they're gone. So that means there is no change in charge because of the equal amounts of ions being missing. However, there is a slight change in density. So these are what we call point defects. The other kind of defect is line defect. So in a line defect, there is a deviation of ideal arrangement of atoms in an entire row or more than one rows of lattices. So a row or many rows of lattices are affected with a defect. These are non-stoichiometric, which means they disturb the stoichiometry. So you get a different formula. So these effects include metal excess defect and metal deficiency defect. In metal excess defect, we have two cases. So one, the anion, which is the negative ion, it is removed, or we have more metal ions, the cations. So when you either remove the anions or you put in excess of metal ions, the cations, you have metal excess defect. So an example for anionic vacancies is LiCl, and an example for presence of extra cations is ZNO. In metal deficiency defect, there is a vacancy of cations or metal ions. Examples include Fe2+ and Fe3+, and this defect can be variable. So therefore, in iron, we can have oxidation states such as Fe 0.95, etc., which is due to metal deficiency defect. This defect is variable. And that concludes the entire chapter of the solid state. We looked at what a solid is, the types of solid, the crystal lattice, which defines a solid, the packing efficiency of these lattices, the voids that are present in between them, electrical and magnetic properties, and finally, imperfections that occur in even the most orderly of crystalline solids. We looked at the different types of defects such as Frankel, Schottky, vacancy, interstitial, metal excess, metal deficiency, etc. And we also found out what are the reasons for these kinds of defects. So that concludes this mind map. We have a lot of mind maps present at Brain Blitz Audios. Don't forget to click on the link of the playlist in the description down below for enjoying more mind maps. If you want to access more of our useful and interesting content, then don't forget to subscribe to our channel, Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.